Okay, I'll begin. Dear Heavenly Father, we thank you for this day. Again, Lord, thank you for these students who just pray to be with us. Help us to glorify you in what we do this morning. Lord, in your name I pray. Amen. Oh, I'm sorry, I left these things on the board. Let me remove them. We still have a little bit more partial fractions to do before we get back to this stuff. So let me see if I can't work out an example or two for you guys. So what we're going to do here today is I'll probably spend another 30 minutes or so on the partial fractions technique. And then we'll turn our attention to section 8.6, which is on rationalizing substitutions. And I'm just going to leave this here. That's for later. Rationalizing substitutions, of course, the idea of that is going to be that we can take other integrals and turn them into integrals of rational functions. But, you know, since we know how to integrate any rational function, or we're learning that at the moment, then we can do those too. All right, so let's see here. Another example. Let me start out with a setup. But do not explicitly determine A, B, C, etc. The partial fractions decomposition for. And it's really important that you understand my instructions on the test. When's the test? Oh, yeah. Soon, right? Like 140 hours from now. Ish. 150? I don't know. Before you know it, though. So it's very important, like, when I tell you something like, but do not explicitly determine A, B, C, etc., and when you ignore me and try to find them, it doesn't impress me. It annoys me because you're wasting your precious time on the test to do that. So if I ask a question like this, you know, it could be something like this: 31x cubed plus 3x minus 7 divided by, let's say, x squared minus 6x plus 9 parentheses times x cubed plus 6x squared plus I don't know, 11x quantity squared. I certainly don't want you to actually find the ABC. I just want you to set it up, right? So there's still some algebraic work to do here. So the partial fractions decomposition is completely governed by the denominator because we have a what? Proper rational function, right? The denominator is 6, it's 8th order. On top we have 3rd order, so it's a proper rational function. And you can factor this, right? This is x minus 3 quantity squared, right? And then what's this? This is actually x times what? X squared plus 6x plus 11, right? Quantity squared. So we can simplify that, right? What do we have? So I've got my x minus 3, quantity squared. When I square a product of two things, like a times b squared is a squared b squared, right? So I've got x squared, and then I can complete the square on that quadratic. I've got actually x plus 3 quantity squared. That's plus 2. All of that squared. Okay, at this point, I've done what I need to in order to see how to set up the partial fractions. Right. Again, we're just quoting a result from the book. It's not something I've derived, it's just something we're using. You might derive this thing in a good abstract algebra course or something. All right, so the partial fractions decomposition for this is going to be something like a over x minus 3 plus b over x minus 3 quantity squared, all right, plus c over x plus d over x squared plus e times x plus 3 plus f over x plus 3 quantity squared plus 2 plus g times x plus 3 plus h divided by x plus 3 quantity squared plus 2 denominator squared. A good check that you understand what you're doing is that the number of undetermined coefficients, all right, what are the undetermined coefficients here? These are the undetermined coefficients, right? I want to leave them undetermined in this example. I just want you to set it up. So there you go, that's the answer. Again, as a good check on this, let me count them. 1, 2, 3, 4, 5, 6, 7, 8. What's the order of the polynomial in the denominator? 8. That will always be the case when you're setting these up. The number of undetermined coefficients must match the order in the denominator. That's a good check that what you're doing is at least somewhat on the level. So any questions about this method before I do another example? Yep.
So on the test we would need to go through this.
That's the answer. That's right. Mm-hmm. Why are you confused by it? Well, that's because this is irreducible. I mean, you could write ex plus f. It would be different. I mean, the book, instead of writing this, he's got ex plus f, right? Basically, this is what the book has. I mean, if I say that this is e bar and this is f bar, there's a one-to-one correspondence between this expression and that expression. The reason I write the one I do is because what I've written is easier to integrate. If you do what the book does here, the term with the e is kind of complicated because it's not just a plain u substitution. If I do this, the term with the e is just a u equals the denominator substitution for an integral. So my way of formatting it is easier when we get to integration than the book. I'm just trying to set you up with a good habit too, because when we get to differential equations and we have to do this thing called the Laplace transform technique, this same approach for partial fractions will serve you well there, because essentially the same algebra happens there for this so-called inverse Laplace transform technique. Like, yeah, we're doing integrals right now, but this algebra I'm showing you and trying to help you learn, this is also important to things beyond integration, this so-called Laplace transform technique. It's important to the analyzing signals and systems for electrical engineers. Something called the transfer function and so forth. So it's not just some silly integration thing. I mean, this is a useful idea for more than just this. Now, it depends on what you're asking. That question you're asking, I don't know what you're really asking. Are you really asking, how do I know that it looks like this? Or are you asking, why did I put that x plus 3 there specifically? Oh, okay. But, I mean, the reason that there's an x in the numerator here, that there's not over here, the difference between these terms and those terms is that these are coming from repeated linear factors, whereas these are coming from irreducible quadratic factors. So it's really a different animal altogether. But only because we're keeping it real. If we did more complex calculations, these things would all become the same and there wouldn't be any distinction. but if I do that, then students complain. So I will not do that. Shall we do an example? How about, what if I want to integrate, I don't know, x to the 6th plus, let's say, x divided by x cubed plus x squared dx. Maybe I should make it more complicated. Let me make it like a little bit more complicated. Let's say x minus 3 times x squared plus 1. That's probably better. I mean, we can do harder examples. This is kind of a slightly middle of the road. Now, what makes this different than the examples I've done up to this point is what we're starting with is what? It's not a proper rational function, right? This is sort of analogous to something like 372 divided by 30, right? That's not a proper fraction, right? So what do? You go, well, I have 372, I'm dividing by 30. So I go, okay, well, I got one of those. That leaves me 72. I got 2 of those, right? That gives me 60. I got 12 of those. Yeah, I'm done. So this apparently is equal to 12 plus 12 over 30, right? This is long division. The same thing goes for polynomials, right? In particular, I can do long division. I can say, oh, but I probably should, I'll do it over here. Let me just one step before I do that. I'm trying to understand what x to the 6th plus x over, and so what's the denominator? I've got really x cubed, right? Minus 3x squared plus x, right? Minus 3. So that's my goal, is to understand how to break this down. The first step in this case is long division. But it's long division of polynomials. But long division of polynomials works the same as long division of numbers, really. So if you understand one, you can understand the other. All right, so let's see here. We're trying to figure out how many copies of x cubed minus 3x squared plus 3x squared plus x minus 3. How many copies of this divisor fits into x to the 6th plus x? All right, so to get x to the 6th from that cubic, what do I need? X squared? No. What times that cubic gives me x to the 6th? X cubed, right. So my first term is x cubed. All right. Now x cubed times this gives me x to the 6th minus 3x to the 5th. Oh no, what have I done? Plus x to the 4th. I had a simpler example in the earlier section. Minus 3x cubed, but we wasted time on other things, so you guys, okay. We'll still get to the good stuff. Then we subtract. We're left with 3x to the 5th minus x to the 4th plus 3x cubed plus x. That x comes down there. All right, how do I get 3x to the 5th from my divisor? Multiply by what? Yeah, plus 3x squared, right? So that gives me 3x to the 5th, and then minus 9x to the 4th plus 3x cubed minus 9x squared. Put some parentheses to remind myself I have to subtract that bottom term in red. Of course, the 3x to the 5ths cancel. and we get 8x to the fourth. Oh, those cancel. Cool. Plus 9x squared plus x. What's my next term? You guys agree? Plus 8x? Looks good to me. All right, so that's 8x to the fourth minus 24x cubed plus 8x squared minus 24x. So help me, if one of you raises your hand in like 30 seconds and tells me about a mistake, back up at the top of this, I will kill you. You should have told me that. Like as soon as you found it, you tell me that. You don't wait. And let me write more. You jump. You interject when I make a mistake here, please. Hopefully, I didn't make a mistake. But if I did, of course, we know that I did it on purpose. All right. So what do we got now? The x to the fourth terms cancel, and we got ourselves a 24x cubed plus x squared plus 25x right? Yeah. So what's my next? So what comes next? Plus, what do you say, plus 24? Man, I should have made this x to the sixth like x to the fourth. That would have been a... But hopefully, I think this serves a purpose. We should all hopefully understand a little bit about long division after this monstrosity of an example. 24x cubed. Fine. Minus 72x squared plus 24x. You guys you're bad people. Minus 72. You shouldn't delight in the suffering of others. It's not the Liberty way. Let's see here. So 73x squared plus x plus 72. Finally, we have reached something which is smaller degree than the divisor, which means we're done. That's the remainder. What does all this mean? What this tells us is that x to the sixth plus x over x minus 3 times x squared plus 1, right? It's actually equal to x cubed plus 3x squared plus 8x plus 24 plus 73 x squared plus x plus 72 divided by x minus 3 times x squared plus 1. Go for it.
In the long division, near the end.
Oh no. Yes?
Where did you get the 24 after you subtracted the purple? Or the 25? Oh, for the x. The last one.
That one?
Yeah.
So that's x minus a minus 24 is 25.
Okay.
Yeah. Phew. Okay, I was worried. So you see where these things are coming from, Mike? In the same way that this long division puts this 12 right here, right? This long division puts this polynomial as the sort of quote-unquote whole number over here, right? Whereas the remainder remains. Just like this. It's kind of hard to see the contrast of 12 and 12 in this example. My luck. Look at my luck. I mean, what a useless example. I've got 12, if not for colored markers, we'd be sunk. But in defensive chalkboards, there's also colored chalk, just saying. But sorry, that battle's been dead here for a while. It's before my time. They got rid of all our chalkboards. They didn't ask us about it, they just took them. It's a sad day for math. Death of chalkboards. Sad, sad, sad. Sorry, I digress. Anyway, are you good? Are you guys good on this so far? Why do we do this? Yep. Excuse me. Minus 3 times 24 is minus 72. So this, what's in black, right, is exactly multiplying 24 times the divisor. And then you subtract it. Now the reason we do this, of course, is that we can integrate the polynomial, right? You can integrate this, 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 and this. Good to go, right? And the rational function that remains, well, this we'll do what? We'll say this is going to be a over x minus 3 plus b bx plus c over x squared plus 1, right? So that's going to be 73 x squared plus x plus 72. And now we got to work that out to finish the problem, right? Let's do that. How do you work out the a, b, and c? This time I'm not going to leave them. Now, if I don't say otherwise, though, you're expected. I mean, if I say integrate or solve this integral, if you gave me an answer that had a, b, and c in it, I'd be like, well, that's nice, but you're not done. See the difference? This one, you're free to be lazy. This one, we have to finish the job. So what's our next move? Whoop. That was not the move I was endorsing. Cross multiply, right? So this is 73 x squared plus x plus 72 is equal to a times x squared plus 1 plus bx plus c times x minus 3. So I will call this thing Pac-Man. Pac-Man is this expression, right? So if Pac-Man eats, let's let Pac-Man eat 3. We get 73 times 9 plus 3 plus 72 is equal to a times 10. So a is equal to what? Because the 3 term dies, right? Yeah, I don't trust my arithmetic at the moment. For shame, I'm using a calculator. Oh my goodness, let's see here, plus 3. I have just lost all respect with a certain generation of mathematicians. So you're 75. 732 divided by 10. So I heard a 73.2 earlier. That was spot on. All right, 732 divided by 10. Now, that just gets me a. How do I figure out what b and c are? What's that? Yeah, that's one way we can do it. I'll do it that way. Follow your lead. So I think what you're saying is I should multiply this out, right? So if I multiply this out, I've got myself ax squared plus a plus bx squared minus 3bx plus cx minus 3c. All right, sorry. I don't have, sorry, poor planning on my part. There. So once we have that, though, we can do things like look at x squared on both sides, right? what's the coefficient of x squared on the left-hand side? What's the coefficient of x squared on the right-hand side? On the left-hand side, the coefficient of x squared is exactly 73. So we have 73 is equal to the coefficient of x squared on the right-hand side, which is just what? A. And, oh, there's also a b. Okay, so a plus b. Oh, but we know what a is, right? So therefore b is equal to 73 minus a, which is 730 minus 732 over 10, which is minus 2 over 10, aka minus 1/5. So there's b. To figure out c, what should I do? We got choices, right? You could look at the linear term, you could look at the constant term. You could put x equal to 0, that's the same. So I'll do the constant term here is a. What else do I got? Minus 3c. Those are the constant terms. Over here, you got 72, right? So that gives us constant, equating the constant terms give us 72 is equal to what? Is equal to a minus 3c, right? So therefore, minus 3c is equal to 72 minus a, which is 720 minus 732 over 10, which, by the way, is minus 12 over 10. Divide both sides by minus 3, I get c is equal to 4 over 10, also known as 2/5. Yes, sir.
Now, could you have also looked at the x term? So
Yeah, sure.
20 equals negative.
Yeah, you'd get 1 is equal to minus 3b plus c. Yeah. You have choices. We could have even differentiated the Pac-Man and plugged in a number, or we could have plugged in different numbers. I mean, there's so many different ways to solve these equations. So just to conclude this, the integral of x to the 6th plus x over x minus 3 times x squared plus 1 dx is actually equal to the integral of what? It's the integral of x cubed plus 3x squared plus 8x plus 24. Right? And then what's next? A was what? Right? Plus 732 divided by 10 times 1 over x minus 3. Then what? I can factor out a fifth, but I won't. Plus parentheses, let's see here. B was minus 1/5. Times x, what was c? So plus 2/5. All divided by x squared plus 1. Now the reason, of course, I've done all this is because now I can integrate. And so the integral actually is 1/4 x to the 4th plus x cubed plus 4x squared plus 24x plus 732 divided by 10 natural log of the absolute value of x minus 3 minus 1/10, the natural log of x squared plus 1 plus 2/5, the inverse tangent of x plus a constant. There you go. Yep. Oh no, where? But I had a minus 12, so divide both sides by minus 3. Minus 12 over minus 12 divided by minus 3 is 4. Mm-hmm. Why is there a natural log there? So what am I doing? So what I'm doing is this is the integral of, like, bring the minus fifth outside, okay? And we have 1/2 du over u, where u is equal to x squared plus 1, right? So that's minus 1/10, natural log of the absolute value of u plus a constant, but that's minus 1/10, the natural log of 1 plus x squared. And that's why that's that. Yes, sir? Oh. Mm-hmm.
Why is it not in the absolute value? The x squared plus 1.
Can anybody tell gentlemen why I didn't have to put absolute value there?
Can't be.
1 plus x squared is larger than 1, so. I mean, yeah, sure, I could do this, but I don't need to, you know.
So it would be correct if you said that though.
It's correct with or without it. It's probably better without it. Other questions? Yes, sir.
The fractional being -1/5 was because you split that up to get the last two putting it away.
Yeah, so I'm basically splitting that into like a minus x over 5 divided by x squared plus 1, and then also 2/5 divided by x squared plus 1. So if I have a sum in the numerator of a fraction, I can split it into two fractions. The thing that you can't do is this. Right? No. Incorrect. Kind of like this. Let's see here. 64 divided by 16. Cancel the 6's. You get 4, right? No. No. At some point this semester, we will have one. I will have a conversation with some student along the effect of, "But I had the right answer," and then I will say, "Yes, but your work was nonsense." And this would be an example of that phenomena, right? Yeah, it's true, but it's also very, very wrong, right? So, yeah. Oh, okay, so let me show you. Yes, sir?
Is the reason why you did long division to make the integration easy?
The reason I did long division is because I don't know partial fractions for improper rational functions. I suppose in principle you could say that, I guess it's the case that if I had added more coefficients, like I could have added like a c1x cubed plus c2x squared plus c3x plus c4, and then plus this template, and then just did one grand glorious algebra problem to figure out c1, c2, c3, c4, and the ABC. But that's not a good move, because if we can divide and conquer, it's easier. And like long division it's an algorithm. It's cut and dried. You know when you're done. You know where you start. You know where you end. It's a nice thing. It's also very general. Long division continues to play an interesting role in like second semester graduate abstract algebra. The Euclidean algorithm is a important thing. So let me show you some examples that I don't want to do in class. Well, yes and no. I want to show you them. I don't want to write them out. Let's say that. I'll just show you guys one of them. You can look at the other ones in my notes. There's a lot of examples in the notes. There's a lot of examples that have the need for trigonometric substitution towards the end of the partial fractions or whatever. But this is the one I wanted to draw your attention to, just as sort of we've been doing these partial fractions where at the end of the process we were able to get by basically just doing ad hoc algebra. We've just been kind of doing hand-to-hand combat with these systems of equations, right? And we have a variety of different techniques. We plug in the zero. Sometimes we equate coefficients. If it's a repeated root, we like to differentiate the equation and keep plugging in the root. That's nice. But beyond that, you know what there's just algebra. So this is an example where that's kind of a necessity. If you wanted to integrate this thing, so I tried to make this example maximally unnice. So to start with, you have to factor this. By the way, factoring, large order polynomials is a non-trivial task. It's not easy. It's not cut and dried. It's a hard problem. And there really is no guarantee that you can do it, at least by hand. So, but this you can factor by grouping. There's an x squared that's common to a lot of things. There's a 9 that's common to a lot of things. And then out pops this x squared plus 4x plus 5. So then you can use the distributive property to factor by grouping. And so this is actually x squared plus 9 times x squared plus 4x plus 5. Yay. Now, once I have that, then I know, okay, so this is the partial fractions decomposition. I got ax plus b, and then cx plus d. By the way, here I'm being inconsistent with my usual policy to, where'd I do it? I've got nothing to show you. You know, a lot of times when I have to complete the square, instead of writing x here, I would write like x plus 2, right? So I'm not adhering to that convention for this example. Okay, now we're on the same page. This is how you'd set it up. Then what's your next move? Same move we make in the examples we did. Multiply by the denominator. Bam. And then multiply it out. Ugh. And so you look at this. You've got cubes, squares, linear terms, and constants. 4 separate real equations. And how many unknowns? 4 unknowns. These will be linear equations. So you have 4 linear equations and 4 unknowns. That means you can solve it. It's just a matter of perseverance. By what? By so-called elimination, by substitution? You were taught that in high school, right? You take one, you look at it, you try to eliminate a variable. That gives you an equation with less variables. Then you try to eliminate the next variable. You keep trying to eliminate variables until you're out of them, right? And then you'll have one equation, one unknown. Then you can solve it, and then you work your way back up. This is the brute force method of solving equations. So here are the equations more explicitly. We have this and that to solve. And so you could keep just basically brute force this. If you tilt your head and squint, you can get rid of the a variable, and then you'll just have b, c, and d. So I get down to this 3 equations and 3 unknowns, right? And at that point, I could use what's called Cramer's rule to solve. I could use Cramer's rule. Cramer's rule says you take the determinant of what you do is you look at the matrix of coefficients for this. So you see that it goes 5. There's 0 c's. There's 9 d's. Here's minus 1 b, 4 c's, minus 1 d. Here's 11 b's, 36 c's, minus 5 d's. So this system of 3 equations and 3 unknowns is the same as this matrix equation. There's something called Cramer's rule, which says you take the coefficient matrix, in this case this. B is the first variable. So what I do is I leave the coefficient matrix unaltered. I take the first column, all right, and I swap that out from this. I replace with this so-called inhomogeneous term. So I put this in the place of that. That's what Cramer's rule says to do. And then you divide by the determinant of the coefficient matrix. Determinant is a specific thing you can do to a box of 3 numbers. I'm not going to tell you. You'll learn it next semester. It's fine. This, of course, example is for breadth, not really something I might ask you this in a homework. Did I ask you this in the homework? Oh, man, I forgot. Oh, don't worry. I'm busy. I don't have time. So you're safe. But I don't know, if I was feeling particularly malevolent, I might put this on a quiz. But I mean, no, I wouldn't do that. I mean, that'd be you'd call me a monster. I don't know. It's just for the notes. Okay, so anyway, that's Cramer's rule, which is kind of nice because it gives you a formula for calculating solution. But it's kind of not nice because the formula is kind of complicated and there's a lot of places to make mistakes. But I know you guys use Cramer's rule in some of your engineering classes, so I mention it to you, all right? This is one of the techniques you'll use to solve circuit equations, this idea. Yeah.
In the test, we have to show our work of solving ADT.
In the test, we won't need these things because have we needed these things up till now? We could do what? We just look at the equations and we get basically isolated equations by just, if we play our cards right, we don't have to do linear, we don't have to do these kinds of tricky things to solve.
Yeah, but what I'm asking is, can we just solve it in scrap paper and then write the answer, or do we have to?
Oh, I want to see steps. Yeah, I want to see steps. That's always the case. But do I force you to do Cramer's rule? Of course not. No, this is not a linear algebra class. And even if it was, I wouldn't force you to do Cramer's rule. So from Cramer's rule, you can get solutions to B, C, and D, and then you can go back and find A. But the best way to solve systems of equations, there's a typo in the notes right here. This REF, RREF is anomalous. That does not belong there. This is by far I think the cleanest way and most general way to solve systems of equations. What you do is you go back up to the original system, you write down the augmented coefficient matrix. This just corresponds to the ABCD equations in the natural way. If you look at these numbers and you look at the system of equations I have at the top of the notes, it's easy to see where these came from. So you write down this box of numbers, you feed it into a calculator, your TI-85 or any of the Texas Instruments, you know, number 40 or higher have this built in. And no one has a TI-40 in here though, right? You have a TI-40?
Wait, no, TI.
Okay, it's 80 I believe. It's been a while since I've seen a 40. Anyway, this is a built-in function for matrix calculators, and or MATLAB. Well, of course, MATLAB or Mathematica, you can just do this without getting into this stuff, or you could just plug the equation into Wolfram Alpha and give you the answer. But this is a nice thing you could do with a lot of Texas Instruments calculators, and this tells you the answer. Oh man, that's a typo. Sorry about that. And there's the answers for the coefficients. Now, my point to you is not that I'm expecting you to do this. My point to you is that as you think about the larger problem of partial fractions, if you work on examples that aren't textbook problems, that aren't, things I would put on a test, you might find the need for some kind of help to solve the systems of equations which come from partial fractions, right? And this is what's out there for you. These techniques and more we cover in the course called either Math 221 or Math 321 here, the linear algebra course. Is about how to solve systems and more generally the structure, the study of linear structure. I have tons more examples in here, but I'll save them for some other day if we need more examples. I'm going to go on now to the next section. Oh, I'm sorry, I should have asked if there's a question about that. Ooh, too late. Sorry. Any questions about any of this before I erase it? Yeah.
So for improper fractions and proper fractions, can we use, can we do this when we have the same number of degrees on the numerator and the denominator, or does it have to be less than the denominator?
Well, in the next example I'm about to work, we'll see what happens when we have the same degree, and when it's equal, you still need to do it. Yeah. It has to be strictly less than for it to be proper. Yeah. Yep.
What's the difference between partial fractions for improper rational and proper rational?
For improper, we first have to do long division to pull off the polynomial part. And then we go back to doing the proper rational, the thing we did last class. So there's just that one extra step of long division. Or a sneaky thing I'm about to show you. You're like, but I thought you said you're going on past. I thought you said you're going on to the next section, so why are you saying you're doing another partial fractions? Well, there's a reason for that. The next section is using a rationalizing substitution to change a problem which doesn't look like a rational function to one that is. So section 8.6 basically is so-called rationalizing substitutions. All right. And so, as I see it, so let me just tell you where we're going, guys. This section, maybe there are, I would say there are really three different problem types. Maybe I count three different problem types. The one is the one I'm about to do. The other one involves exponentials. And the third one is the so-called Weierstrass substitution, which I've left from the previous class over there. Those are really the three, it seems to me, at least as I look at the section at the moment, those are our three main tasks, is to kind of come to grips with the idea of these substitutions. And these might seed our imagination to do a wider class of integrations, perhaps. But certainly these three are our starting point. Now, once that's done, that's pretty much it in terms of integration theory. There's nothing else for me to teach you, really, in terms of basic integration techniques. Integration techniques beyond sections 8.1 through 8.6, what else is out there? Well, past that, there's the study of differential equations, which in some sense is generalized integration theory. So yeah, I mean, fine, differential equations in some sense is integration. Or you could say that what we're doing is elementary differential equations. You pick it. But that's kind of it in terms of integration theory. So what's left to do then is the numerical integration. That's what we'll probably do tomorrow. Numerical integration is just totally different. There's a few simple rules we'll learn that allow us to approximate integrals through specific kinds of sums: left point, midpoint, right point, Simpson's rule, trapezoid rule. That's about it. But they're not learning so much a technique as you're learning a formula per se, and to really implement it, it's almost the case you have to use technology to really do it justice. Yeah, any question? So it's kind of sad. I mean, we're kind of out of integration techniques. I mean, but that's kind of it. Yeah. It's explained in the course planner. So the course planner basically says up through numerical integration. But yeah. Okay, so example. Let's get to it. How would you integrate something like dx over 1 plus the square root of x? So here's what we do. What we do is we say u squared is equal to x. Now if I do that, that says that x is equal to, well, that says u is equal to what? Square root of x, right? And what's dx equal to? Well, 2u du is dx, right? So here's my little thought bubble. That's the implicit substitution I'm making. And what am I left with? I'm left with 2u du divided by 1 plus, what we got here? U, right? Now this is that example I was promising you a minute ago. Now we have linear over linear. There's two ways, I know two ways to do this calculation. I'm going to show you both. The first way I'm going to show you is my trick. It's not really my trick. I don't know who first did this. Who knows? Probably Euler. Euler's a pretty safe thing to say about anything like this. So 2 times, or anything really, 2 times u over 1 plus u. But what I want, right, is I want 1 plus u up here too. See, I have to put a 2 there because I've got a 2u up here. And I want that 1 plus u because then it will cancel with the denominator. But by doing that, what have I done? I've added a 2 that wasn't there. So what do I have to do to be fair? Subtract 2. Yeah, subtract 2. And there you have it. This is the integral of 2 minus twice 1 over 2 over 1 plus u, parentheses du. It's a sneaky adding 0 trick. It works especially good in the case that you have equal degree in the numerator and the denominator. Of course, we could use long division just the same. You could even use synthetic division, but I don't even know how to do that, so I'm not going to show you. Let's see here. So I am dividing 1 plus u, that's my divisor, into 2u. So let's see here. I'm going to write u plus 1 rather. Easier to think about. So that gives me 2. Then I got 2u plus 2, which gives me minus 2 is my remainder. So therefore what? Therefore 2u over 1 plus u, in fact, is equal to 2 minus 2 over u plus 1. As you can see, that and this are the same bird. So if you don't like my trick, you could do long division. It's up to you. You got to do something, otherwise you can't integrate. I suppose you could still integrate if you make a w substitution or something. Anyway, this is one way to do the integral. What do we get? 2u, right? Now I can safely omit the absolute value bars here because it's pretty clear that 1 plus u is positive. So the absolute value bars here would be redundant. And then I'm not done, right? I have to go back to what? X. Yes. So this gives me twice the square root of x minus 2 times the natural log of 1 plus the square root of x plus a constant. There you go. Yeah?
So your original, the point in making a u squared was to get rid of the radical.
Exactly. So the game is to eliminate the radicals. So let's see here. Next example. So I got myself a cube root of x plus the square root of x. Another good example to look at. So what do you guys think? We want to put all the radicals in jail. Don't want to let them talk. It's not safe for society. It's not a safe space for the rest of us if they're out. To jail them. What power should we raise them? I would respect your answer. If you say there's no such thing as a safe space and that's nonsense because we have this thing called freedom of speech, then I would agree with you. But still, we should do this example. Let's see here. I heard a sixth. Why would you use 6? Right, 6 is 3 times 2, so it's going to kill the cube root and the third root. Let's see how that works out. But admittedly, you probably just guessed that, right? And that's fine. Did you guess it or did you work it out? You worked it out. Oh, how did you work it out? Did you guess like an arbitrary exponent and then see what you needed? I mean, I'm curious.
3 times c.
Oh. Never mind. It's fine. So let's see here. X to the 1/3 power is what? It's u to the 6/3 power, right? Which is what? And then x to the 1/2 power is u to the 6/2, which is u cubed, right? How is dx? What's dx? Excuse me, 6u to the 5th du is equal to dx. So there you go. There's my thought bubble. Let's put it into practice. What we got? We got integral of 6u to the 5th du over u squared plus u cubed. So can you guys help me simplify that before we do anything much more? You can divide the top and the bottom by what? U squared sounds like a good idea. So upstairs we're going to have a 6u cubed du divided by what? Divided by 1 plus u. See, I knew these examples were coming today, which is part of the reason I didn't do more long division earlier, because I knew these would give us more practice with long division. So here it is, right? Here we go. One more time. So you're dividing, our divisor is u plus 1, and we're dividing it into 6 u cubed. I suppose you could leave the 6 out of this. It would be easier. Oh well, too late. So this is what? I got a 6u squared. Yeah, it would have been smarter to factor the 6 out to start with, but oh well, too late. So that gives me minus 6u squared. What's my second? What did you say? Plus 6u? Or minus 6? Minus 6u, right? Then what? Yeah, plus 6. All right, so this gives us then, in fact, we can rewrite this as the integral of, let's see here, we got what? We got 6u squared minus 6u plus 6 minus 6 over 1 plus u du. I'm going to go ahead and factor the 6 out like I should have done about a minute ago. So factoring the 6 out, we got what? We got 1/3 u cubed minus 1/2 u squared plus what? Plus u minus the natural log of 1 plus u plus a constant. What's u equal to here? Add something to the thought bubble. U is equal to? Yeah, 6th root of x. There we go. Okay, so there you go. This is 2. U cubed was what? U cubed is square root of x. U squared was the cube root of x. U was plus 6, the 6th root of x, minus 6 times the natural log of 1 plus the 6th root of x plus a constant, and there you go. Es bueno. So you kind of get the flavor of these kind of substitutions. You can eliminate radicals in algebraic expressions. Make sense? Hopefully this is enough for you to see how to do the homework from section 8.6, which is like this that I've assigned. Assuming I've assigned some. Who knows, I might have forgot to. So that brings us to the Weierstrass substitution. Weierstrass substitution is, well, due to Weierstrass. I don't think your book calls it this. Weierstrass, famous 19th century mathematician, one of the fathers of modern analysis, introduced this notion of uniform continuity, which is very useful to understanding the convergence of things properly, and important figure in 19th century mathematics anyway. And he also left us with this little trick. Although I honestly think, I don't know, I have a hard time believing just this guy did it. I don't know, I bet more people knew about this. I don't know, I'm not a historian. But here's the substitution. U equals tangent x over 2. That's the substitution. Now the reason to do that is it will allow us to convert sine and cosine to rational functions of u. So here's how it goes.